This video is sponsored by PCBWay. More of that later. There will be a time in your life as an electronic something when you need to determine a logic level of a pin. Well, say you've written something that should blink and you want to make sure that it blinks. Well, how do we do this? Easy peasy, you say. Well, let's try this. I use my trusty multimeter, the one I stole from Richard, more or less. And let's see if I can see the frequency there. Well, this is something not a logic level would say. Did I mention that the frequency on this pin should be around, say, 5 Hertz? Yeah, and my multimeter is obviously not capable of measuring this, so we need something different. Look at this clever thing. These are 8 LEDs in a row. The anode is to plus. This is a red wire that's over here sticking here. And the cathodes are on this pin headers over here. So I'll use this little LED here, and this is connected to this one, this little thing here. The cathode is on the green wire. So let's plug this in and see if we can see something with an LED. And if I move my hand out of the shots, we can see blue lightning, blue blinking. And yeah, this is a good start. This tells us there's something going on. But still, does we have correct logic levels? I mean, this could be something that simply pulls to ground and switches to tri-state, so you won't see a high signal there. Well, we still need something different, right? Right. Of course we can go scope, but this is a bit overkill, don't you think? I mean, you can use any scope. This is the one I just had laying around. And to just see the waveform, there must still be an easier solution for that. And there is. The thing we're looking for is called a logic probe. Well, the name gives it away. It probes for logic levels. So you can get it in the, well, cheapo Chinese version, which trademark is that the faceplate always falls off, so you have no idea what the switches are for. And you get the way more expensive one. This is this one here from I have no idea what the firm, what the company is that does more fancy stuff here. But in the end, we only want to know what the logic levels are. Well, speaking of logic levels, what are logic levels? For the majority of us, so I count you in there, 2 logic levels are really important, 5 volts and 3.3 volts. Yeah, I know there's 1.8 volts and some special voltages around V-cores of a graphics card or a CPU in a PC. But for us normal people, 3.3 and 5 volt do the trick. The good folks over at Sparkfun had this nice little chart over here where you can see what logic levels are. So everything below 0.8 volt is low. So 0.4 is low, 0.5 is low, everything below is 0.8. And to do a definitive thing over here, everything above 2.7 volts is high. Nice. Okay, this is a pretty good example. What's with the space in between? Well, that's undefined, or say bad. You don't want to go there. You want to have a stable signal above 2.7 or below 0.8. So this is a 5 volt logic. Let's see, well, if I scroll down a bit here, there comes the 3.3 volt logic. And interestingly, the low signal is the same. Everything below 0.8 is the same, so we're fine there. And to have a definitive high level here, everything above 2.4 volts is high. If I threw these two diagrams together, I could say everything below 0.8 is low, and to be on the safe side, everything above 2.7 is high. This would give us a really good matrix here to find out we could do a window with that. By the way, for the 3 volt 3 thing, in the middle is again undefined, i.e. bad. So how can we detect if any given signal is below 0.8 or say above 2.7 volts? Do we need a microcontroller for that? No. In fact, we will do this without a microcontroller. I know you think that is going crazy. He does something without a microcontroller. What's going on here? Cats and dogs living in peace. There's a pretty nice learning effect here. Let me show you. Oh crap, the left-handed guy is drawing stuff again. Please stay with me, come on, this is going to be interesting. And in fact, this is going back to a design I did in the 1980s. Yeah, back when I was young and there were no microcontrollers around, and I still think this is a pretty clever one. I haven't seen this around, well, no I haven't. And I'm pretty sure I didn't copy it, I think. It all revolves around operational amplifiers. Or the normal short term is op-amps. An op-amp is a simple device. It's an amplifier with a theoretically infinitive amplification factor. So for example, if I would tie minus here to ground, put some signal onto the positive input, I should have something like that. Because it's infinitive, so even the slightest variation would turn into a infinitive amplification. The plus and the minus over here means non-inverting and inverting input. Let me write this down. So as you can imagine, the non-inverting input keeps the signal form. The inverting input would turn the signal 180 degrees on top. So let's play around with the idea. Say we put 3.3 volt on the non-inverting input and put 3.0 volt on the inverting input. The non-inverting is way higher, 0.3 volts higher. So this is an amplification of infinity, so we will get VCC, whatever the VCC, the power supply of the op-amp is. If we turn this idea around, say we put 2.4 volts on the non-inverting and put 2.8 volts on the inverting, we would get GND or whatever the ground potential on the op-amp is. This mode is actually called a comparator. So because it compares the both inputs and gives you an output for that. We have a fairly digital behavior here. The op-amp is normally designed for analog stuff, but we're using it as a very digital comparator between two voltages. So if we would use two op-amps who could detect a high signal, say everything above 2.7 volts, and a second op-amp who could detect everything below 0.8 volts, well, that would be a thing, right? Okay, let's draw a little schematic for that. Yeah, I know you were panicking that I would try to draw this by myself, but there are simulators out there that really can do this. This is Falstad, and this is free, and it's a web application. Everything nowadays is in the web, and this is really great to try stuff out, and well, yeah, it's really great. I really love this stuff, and I use this pretty much, if I do in a design with some analog thing in here, I pretty much do this all the time. So what do we have here? They are my operational amplifiers, and you can tell they are connected over here. These are some LEDs here. You can see one LED, two LEDs, so they anti-parallel. So if the signal over here is positive over here, we have this LED will light, and the positive signal coming from here, this LED will light. The other one will stay low, and we only need one resistor here, so fine. Over here is my input. This looks a bit strange because I needed a way to simulate a contact, because no contact right now, and then I needed to switch from 5 to 0 volts. This little switch does this. So now we're having 5 volts on the input. You see the green wire over here. If I switch it down, we have a 0 or a gray one over here. This is a resistive divider between 5 volts. This is my supply voltage, say USB, and ground. So this is a resistive divider that will clamp this point over here to 2.5 volt. If you follow the lead over here, lead, you see this is going to 2.5 volt right now. And there's a second resistive divider with 3 resistors over here. And the beauty of Falstad is I can let them show which voltage is on a piece of wire over here. So I know 5 volts come in over here, 51K, 47K, 20K. And on this point over here, so the lower one over here is 847 millivolts. And this is pretty much my low signal. And on the upper side over here, I have 2.8 volt. 2.8, I know we said 2.7 would be great. Well, with this resistor divider, 2.8 was the one I could get with normal resistors. Normal resistors you get in a shop and without doing trim ports and stuff. And I think 2.8 is still fine because everything's higher above 2.7 will make the signal more definitive. So let's try this out, shall we? So this switch over here simulates simply I touch a pin. So I'll touch a pin right now. We have a ground over here, so let's touch this. The ground signal goes through the switch, draws this point over here right to 0 volts. So now both of our op amps see 0 volts, one on the non-inverting and one on the inverting input. So now we have the red LED, this one, and it tells me, okay, this is a low signal. Because low, right, you know, if I switch this switch over here to high, let's do this. This point gets pulled up to 5 volts. And now the upper comparator gives me a high and the green LED lights. If I drop my supply voltage over here to say 2.3 volts, gotten this, see, 2.3 over here, and none of the LEDs now lights because this is not in the range of these comparators. So this is exactly what we want to have. Should we build it? And before I hit you with some schematics and some Gerbers, here's the little bugger in action in real life. And let me tell you, this is an old design. I did this probably 3 or 4 years ago. And if you're wondering, where's the freaking chip? Well, turn it around. This is a two-sided design, so 2021, there it tells. So 2 years ago, just to prove that this works, let me connect the little one to my blinky pin over here. Can you see this on camera? No, it's gone because this is not a good connection. Of course it isn't. And you can tell there's a high and low blink. Yeah, this is what I wanted to see. Perfect. All right, let's get over to some schematics. And here's a real-world schematic, so let's have a look at this. I choose an LM358 as the operational amplifier. This is a bread and butter op amp. You get this everywhere. Should be easy to get in whatever package you want to have it, if you don't have it laying around, because normally you do. The more interesting part will be the USB male port here. So this is a USB plug, and there are about 1 million variations of this available. So if you have some laying around and they won't fit, simply connect VCC and ground to a USB plug cable, something, and you're fine. This could be hard to find. I'll leave a link in the description for an AliExpress thing for that, but no guarantees if the link survives or if this is really a fitting one. I included a little power LED, so if you don't want to have this, you could leave this out. It won't hurt anything. But I'm fine with having a little power LED. They're telling me, oh, the little circuit is running. Over here are my two 47K resistors that clamps the input signal to a defined VCC half. So this is normally 2.5 volts. And whatever you connect the probe to, it will pull it into plus or minus direction. Here's the triple voltage divider, so 2.8 volts here and 0.8 volt over here. There are both my operational amplifiers. The clamped signal from down here goes one to the positive and one to the negative point. And there are my two LEDs, anti-parallel 1K resistor to limit the current. I included a little socket over here so you can grab VCC and GND from the USB port, or you can power this over here. If you don't have a USB port enabled, you can simply throw over here VCC and GND on this one and it will work too. And I know you're already saying, oh no, this is all SMD, so I will never build this because I hate SMD and this is so fiddly to work. Don't fear, young Padawan. See the 3 mil over there? This is an through-hole version, because you get all the parts in through-hole. The LM358 is available as a dip package. The LEDs are 3 mil now, and all the resistors are standing up because I wanted to save some space over here. There's my probe connector, so you can put a wire on there, you could put a pin header on there. VCC and ground as headers over here. This is a USB plug, and nothing special happening on the backside, so pretty boring stuff over here. And for those people over there who says, no, this is so big, I want to have my stuff in SMD. There you go, my friend. This is the SMD version. I've chosen to do this time one-sided only, so because two-sided, If you want to get this assembled by PCBWay, this is complicated. If you want to have it on two sides, it will get really expensive. So this way around, you simply drop them on the top side. All these resistors, all these LEDs are 06, 03, so barely human solderable. This is doable. You don't want to really get smaller. Well, I don't, but this is doable. I was thinking about 08, 05, but this what came out of it. And this thing is tiny. So you have 33 mil by 15 mil, or for the thrower version, 54 mil by 15 millimeters, I should say. So really, really, really tiny. So one thing left to do, right? Order PCBs. And this time I'm going to play around with the option to let this populate by PCBWay. So if you want to have the SMD version, but you don't have fun or don't want to try out soldering SMT, this is a way for you to do that. Let me show you. If you're on the start page and I'm already logged in, you simply go for quote now. And don't mess around with this stuff. Go for quick order PCB. Here I can add my Gerber file. And I'm choosing the SMT version over here. And there's my Gerber. So scroll down a bit. I like my PCBs not in 1.6 mil. This is way too heavy. And for this little board, 1 mil will be fine. 1 millimeter, I should say. Traditionally, black, of course. If you want to have the PCB assembly service in your order, this is down here where it says assembly service. Just check the box over here. And well, let me get back over here. I'm ordering 10 PCBs because I want to have 10 PCBs around, but I only want to have, go back, wait, wrong thing. I'm ordering 10 PCBs over here. But I don't want to have only 5 of them assembled, because I want to have 5 to play around. If something goes wrong, this is the right way to do this. I know that I only have components on the top side. I want to have them as single pieces, and I want to have them turnkey. Turnkey means PCBWay does everything for you. They order the parts, they get the parts if they don't have them available at their store, and they assemble everything. So you get everything ready to roll. One thing I do in here, do you accept substitutes made in China? Of course I do, because for a resistor or an LED, that doesn't matter. So now I'm fine. I am going to save this to card. And my order now is under review. That means they're checking my order. Currently, I can't start the order because I need to add my files first, because I have the Gerber uploaded, but I don't have my BOM uploaded, and I don't have my pick and place file uploaded. So I get my BOM. They are all in the same folder, by the way. So my thing over here, this is LogiProbe, SMT version, come on. And this is a BOM, bill of materials. And I need to upload my Centroid file. Centroid means pick and place. Other design software calls this pick and place. So, and then I can say, okay, submit order. And now PCBWay has everything they need from me. This is already done. The 30 euros that you see over here, $30 you see over here, are a guesstimate. Right now they can't tell you what this really will cost, because they need to check what every component will cost. Imagine I have a CPU on there that costs hundreds of dollars. And this will change when the audit of the order is done. And then I can do, where's the thing? Somewhere there must be a processor checkout, which is now grayed out. This is a way to order assembled PCBs. Easy peasy. And if you want to have more of them, this is actually a very cheap way to produce a number of PCBs without sitting weeks and weeks and weeks with a soldering iron and trying to fiddle this out. Once again, thanks PCB for sponsoring this video. So that's it from me today. I use this tool really quite often. This is one of my tools that's always around while I'm developing stuff. I really don't use the boat ones. This is my normal go-to tool here. So let me know in the comments if this was useful for you. if we would say, oh, I'm going to build one myself, or I'm going to do a breadboard version, or I do want to do this with a CPU, yeah, component count would be a little lower. But I really, really like this adventure into doing something analog without writing software. And yeah, sometimes this is cathartic. So I hope you learned something today. You had a bit of fun with me. And yeah, I'd see you in the next video.